A very good afternoon to the lecturer. My name is Krishna Muniandy, MA18219. Today, I'm here to present my project-based proposal writing title, The Effects of Acoustic Frequency on Oscillatory Flow in Thermoacoustic Refrigerator Using Particle Image Velocimetry. First, to understand the project, we need to understand what is thermoacoustics. Thermoacoustics is the interaction between heat and sound. So, a thermoacoustic refrigerator is a type of refrigerator that uses thermoacoustic principle. The lower efficiency of thermoacoustic refrigerators are due to the high sensitivity and to the input parameters. There are two types of thermoacoustic refrigerators, which are standing wave and traveling wave. For this study, we will be using standing wave. So for the problem statement, we are here. This project is aimed to observe how the difference in stack length can affect the oscillatory flow. We need to observe the oscillatory flow, which is done using a particle image velocimetry. By solving this, we can lessen the cost industry spend on the cost of electricity for the thermoacoustic refrigerator by increasing the performance of thermoacoustic refrigerators. Next, a project needs objectives. So the two objectives for these projects are to observe the relationship between the different stack lengths and the effect of on the oscillatory flow of the thermoacoustic refrigerator using PIV. Next, to investigate the effects of oscillatory flow to the thermoacoustic refrigerator by calculating the coefficients of performance. So we from this project are aiming to answer two questions. What is the different effects in this oscillatory flow caused by the stack length, and what are the effects of the stack oscillatory flow on the performance of a thermoacoustic refrigerator? So from this study, we know that refrigeration is very important for humans, and there is a greater demand for more efficient and environmental friendly cooling nowadays. This study will help the industries to have a more efficient thermoacoustic refrigerator in their production. And for ordinary people like us, a thermoacoustic refrigerator might replace conventional refrigerator if it becomes more efficient. So from this study, the expected outcomes are to find the most optimum stack length and to study and to get a better understanding about how the stack length and the oscillatory flow works in interconnected are interconnected. So a thermoacoustic refrigerator has four parts: a driver, a resonator tube, a stack, and a heat exchanger. A driver is connected to the resonator tube and is tasked to supply with frequency input, mostly using a frequency generator or a power amplifier. The next part is the heat exchanger, where it gives a purpose for the thermoacoustic refrigerator by making it either a heat pump or a refrigerator. The stack acts as a heat gradient for the thermoacoustic refrigerator. Next, let us see what are the effects that affect the oscillatory flow and performance studied by that we got from the past studies. Some of them are working gas, operating pressure, frequency of loudspeaker, resonance tube shape, length and material, stack length and position, and stack geometry and material. We will be focusing on stack length and position. So to understand about the oscillatory flow, we need to measure the velocity profile. To do this, there are two ways: simulation-based and experimental-based. For this experiment, we will be using experimental-based velocity profile measurement. And from those three, we will be using particle image velocimetry. So a particle image velocimetry is a precise measurement tool which measures and observes the velocity profile. There are three main components of a particle image velocimetry, which are the high shutter speed camera, which is also known as CCD camera, and high power laser, and a synchronizer. A synchronizer is used to synchronize the frequency between the CCD camera and the laser. Next, for the gunshot, we will be seeing through this gunshot how the project will progress. Now we are at the proposal presentation and approval. Before this, I've already done by identifying the problem statements and objectives, and I've already done past studies, literature reviews, and I've already done the research design and setting the research parameters. After this approval, I'll be procuring experimental materials, which I've already started. And after procuring the materials, I'll be doing the experiment itself and doing some data analysis. And lastly, I will compile the data and present the findings and publish the work. Next, to understand the experiment, there are two types of setups in this experiment. One is a thermoacoustic device, and another is particle image velocimetry, which is a PIV setup. For the thermoacoustic device setup, it is already in the faculty, so we will be using the same thermoacoustic device with a few changes. The changes that were made is that the resonator is changed to a length of 20 centimeters and is made from ABS. The stack is also made from ABS. This is because ABS has low thermal conductivity, and low thermal conductivity is important so that there's no reverse cooling effect. The initial desired stack has a diameter of 65 mm and a length of 45 mm. Each fin in the stack has a thickness of 0.5 mm and the distance is 1 millimeter between each plate. So this is the particle image velocity setup that we have in our faculty. So for the signal resource, which is the frequency generator that we will be using is AFG 2000 series arbitrary. And the seeding particles which will be used as velocity indicators are silicon oil fog, and the silicon oil fog will be made through fog generator. Next, the laser is a 532 nanometer wavelength laser, which has a repetition rate of 15 Hertz, and the camera is an Imperex ICL B1620. We use a dual camera system for this PIV, and the camera setup is installed on a multi-axis tripod so that we can adjust the X, Y, and Z coordinates for the experiment. Next, to do the experiment, the CCD camera has 44 frames per second repetition rate, while for the laser it has 15 Hertz. So we can't make synchronized measurement of the flow. So to do that, we need to use a new method which is called phase averaging method. To do this, we need to subdivide the acoustic cycle, which is 360 degrees, divide it by 15 degrees, and we will get 24 equally spaced phases. Next, we use a synchronizer to synchronize both the camera and the laser and do multiple shots of the same phase to get an instantaneous velocity, which will be analyzed through Dynamic Studios version 3.04, and we will get the velocity maps. Next, few parameters will be fixed so that the experiment can be more accurate. Some of them are the working fluid is air, the working temperature is 25 degrees Celsius, the working pressure is 1 bar, ascending wave thermoacoustic device is used, the stack and the resonance is made from ABS, PIV is used. Each time the PIV is calibrated at the same spot, a dual lens system is used, silicon oil fog is used, the experiment test bench is the same experiment test bench is used, so to reduce the possibility of error, and the data processing is done in Dynamic Studios 3.4. To do this experiment, first we need to calibrate the camera and lasers to the position where the stack will be placed. To do this, we will be using a calibration plate. The calibration plate should be a length of 75 mm by 45 mm. It should be placed 30 mm deep so that all the stacks can be measured during the PIV measurement of the real stack. So to do this, we need to align the laser and camera on the same plane as the calibration plate. This can be validated through the Dynamic Studios. After the alignment, the calibration plate is replaced with a real thermoacoustic setup, and the position is validated again. This is a setup of the project that we will be doing. So this is where the calibration plate will be, and the stack will be. This is the thermoacoustic refrigerating setup, and this is a PIV setup. The frequency setup is where the frequency is supplied to the driver, which is the loudspeaker. Next, for any projects, we need to have two variables. One is a variable that needs to be changed, and one is a variable that needs to be measured. So for this, the variable that needs to be changed is the stack length. The first initial stack length that we will be using is 65 mm length and 45 mm diameter. This is because the resonator of the our thermoacoustic device was built for this dimension. In 2017, Kajura also did a similar experiment using 4 main values of the stack length. Their device was made for 105 mm, and they used 110, 120, and 130 mm stack length. So which has an increment of 5 to 10 mm. So for this experiment, we will be using 65 mm, the first initial value, 70 mm, and then 75 mm, which has a increment of 5 to 555 mm. So the second variable is the variable that needs to be measured for this project. The velocity profile of the acoustic oscillatory flow needs to be observed. To do this, we will be using a PIV, and it needs to be analyzed through the Dynamic Studios version 3.4. The data are plotted in a graph of 3 variables where frequency, velocity, and oscillatory flow is needed so that we can calculate the coefficient of the oscillatory flow. For the qualitative evaluation, the images and videos of the flow movement captured using the PIV device is studied. The behavior of the flow is studied and compared to other frequency data that we have got from past studies. From this, we can determine which is the optimum stack length that can be used for a thermoacoustic device. So this is basically all for my project proposal, and I hope that you can understand this project and approve this project, as this has a lot of implications on this society and for the future. Thank you very much.